one of the fundamental data structures that I designed and implemented for Redis are streams. I always liked a lot append-only data structures, even just files. Append-only data structures are extremely powerful for a number of use cases. But especially for streams, I remember that I became fascinated with the append-only data structure idea in the context of Kafka. Not because I was a user of Kafka itself. I never used Kafka in my whole life. I don't know how it behaves, how it works. But I read a few blog posts that basically extracted the fundamental idea about having a log of events, and I liked that a lot. And I said there is fit for Redis to simplify a lot of this kind of design, to make it Redis-alike. So I started to design and implement streams. And then I left for 5 years the development of Redis, and I completely forgot. And I understand this is not very humble, but then when I today rediscovered streams, and yesterday during these 2 days, I said, this is really cool. I mean, it's a very good design. I don't like everything I made. So this is one of the cases where when you look back, you say, oh, this is a good work that I accomplished. And today I want to show a bit a use case that I have for streams, and also want to show how they are implemented, why they are so memory efficient, and why their design, I believe, is so good to work with, so easy to understand and useful. Let's start from the fact that I have installed solar energy power in my roof for a total of 8 kilowatt, and I have a battery of 15 kilowatts. And the idea is to be a bit more energy independent, to help the environment, a mix of things, because you know this is a very long-term investment. So you recover the money you spend after 5 years, 7 years, 6 years, 4 years, depending on how much energy you use. We use quite a bit of energy in my house. However, for 3 or 4 months every year we go to the seaside. So this cuts significantly the total energy that we use, but still it is possible to sell this to the grid, even if each kilowatt is paid just 10 cents or something like that. But all in all, we wanted to do this. And I discovered that even if inverter is in theory a German brand, Weissmann or something like that, actually it is a Chinese white label that was rebranded with the logo of the German company, but it is Chinese. And it's a very good Chinese product, which is called GoodWe inverter. And it has an open port without any authentication whatsoever. Security 0, but anyway, the protocol is documented. It's very easy to access via UDP or something like that. And there is a library that works very well, and so I can extract all this data. And every 15 seconds, I send this data to a Redis stream. So later, in this Telegram bot, because the software that they give you, it's not great. Also, it's very basic. It's conceived to be watched by people that don't know what a kilowatt is, don't know how the energy balance works. So I wanted to do something more interesting. So I wrote this Telegram bot, and I tried to come up with a better way to visualize energy balances. So I did this graph. The idea is mine of the graph, but oh sorry, when I zoom this, it is no longer possible to. Let's do differently. So Python 3 plot graph. Okay, this way I can resize the window, and it is much better in this specific case. And I think in this way I can even zoom and so forth. I designed the idea of how the graph should be plotted, and then I asked Claude Sonnet to write the code for me, because these matplotlib libraries for Python are very useful, and at the same time are some kind of programming torture, just boilerplate after boilerplate that I don't want to write. So in this case, AI is a blessing, because it's very low quality coding task. So basically you have the x-axis, and above the x-axis you have the sources of energy. I have two different strips of panels. One is facing ovest and the other east, more or less. And as you can see, initially the east facing the east facing panels produce a lot more, and then as time passes the things is reversed and so forth. So we have basically the two greens are the sum of the energy produced. Take in mind that I am in Sicily, and here solar works very well, much better than in the rest of Europe, of most of Europe. Greece, south of Spain, Portugal are similar, but otherwise it's like the best you can get. However, you see here those are clouds here. Then you see it dropping. Why? Because under the x-axis you see the loads. So initially we have the house itself. Here you can see house consumption, which is the gray area, and then you have the battery charging, which is the battery is shine on the energy provider side, and blue on the energy load side. But when the battery charges fully 100%, since still for a matter of paperwork, basically contracts, stuff like that, I am still not authorized to exchange the power that I have a surplus for with the grid. Then the inverter drops the production and will just match the need of the house. So you can see that the graph is basically symmetrical. It will not be symmetrical only in a specific case, which is when I can export the energy, and then you could see here, oh, but it will be anyway symmetrical, because if I can produce more, then I have here the pink area, which is grid export. Another thing that I noticed is that the battery during the night has cycles where it goes to 100 watts, and then the rest of the energy is provided by the grid, like if it's a resting mode or a calibration mode or something like that. I don't know. Anyway, this graph is generated using Redis Streams. Let's see how the data injection works. Energy data, energy model, GoodWe data collector. Okay, we use basically the GoodWe library to extract the data, and then we import Redis. and we have two keys. One we log every 15 seconds in the first stream, and in the second we log hourly, because in the 15 seconds stream I put less data, but the data that I want with a very good granularity resolution, and then in the hourly I put a lot more, but it's more sparse, so it's not a problem for the memory and so forth. And then there is this command, which is Exad, that inserts the element in myStream. But to see how a Redis stream works, I have just two keys here. We can use xrange in order to extract some data from this. Let's use revrange, which is a range that takes the end and then the start. So I can say from the end of the stream to the start of the stream, count 1. Okay, basically streams are an append-only data structure. However, every time you append, your new entry, which is each entry is a set of key value, key value, key value, gets assigned a unique ID. This ID is a bit special because it's the millisecond Unix time, and if you generate more than an event in the same millisecond, then there is an incremental number. And this is extremely useful because you can provide basically ranges that are already with time, and it will extract items. However, there is also this special plus and minus, which means the highest ID that you have and the lowest ID that you have. So here I'm showing you the last entry. This is the first string of panels, the second, the total, temperature, how much the battery is providing energy, almost 2 kilowatts right now. Yeah, because outside is dark already, and but we should be able to see that if we plot the graph. Yeah, exactly. As you can see, let's zoom here in this part. Now the battery at the green stopped a few minutes ago, and then it's all battery energy, this color here, that matches perfectly the house energy. It's very cool, I must admit, even if the saving maybe it's not great or it's in the long time. However, if you do the math, it's probably a better average investment in long term, in 10 years, than the SP 500. So back to the vectors. You see it's key value, key value, key value. And how many items I have here? It's 1 day and a half that I have this running, something like that. So memory usage, let's see how much memory the key is using. Just 300k. And this is very interesting because if we do the math, we discover that since we have this memory usage and this number of entries, that we are using just 49 bytes per entry. And you can wonder how this is possible, because there is a lot going here. The ID and all the fields and the values, and even if you like cut this, concatenate this as a unique string, is a lot more than the number we are seeing here. And the point is that streams are implemented using a set of interesting techniques. Let's go to check such techniques. Okay, we want to check the Exad command, the command that adds a new item. By the way, this command works like that. Exad, the key, then you tell it the ID, okay, but normally you use this as ID to request the next ID, calculate the ID yourself. It's up to the server, and there are and then you say key value, key value, key value. Let's see here how Exad is used. Okay, this is like a higher value, a higher level interface of this. I want to show you Exad Redis example. Let's see if there is some example here. Oh, perfect. So Exad myStream, and in this case I am specifying a specific ID. I can do that, but as long there is however a contract that we must specify an ID which is always increasing. Exactly. Normally you use them like that. Exad myStream. I can do cut and paste here, I believe. Yes, exactly, and you get the ID returned. But let's see why this is so efficient. Exactly, yeah. Basically what happens is that stream append item, okay, we'll calculate the next ID, then it will return, check that the new ID is greater than the last entry ID or return an error. So there is this rule enforced because it's an append only data structure. So the invariant here is that we must append greater things. I avoid overflow when trying to add an element to the string and so forth. Okay, that's the point. Let's see what we do here. We seek the last entry, okay, to calculate the ID. But the important thing is that it's basically a Radics tree of the IDs. However, for each ID, we don't have just a single entry, but we have a blob containing multiple items. So the new Listpack, we create a new Listpack, which is basically a data structure that Redis uses, and we will see in a moment. Consider it as a compressed linked list with certain features, which is basically a linked list without pointers. It's just an encoding basically with key value, and key value. Redis uses Listpack when we don't want to pay the cost of a hash table or something like that, and we have, for example, an hash which is small, and we use this compressed view of the data structure. Then if we accumulate too many items in such data structure, we promote the list back to the actual data structure that can represent this data type with the specified big O complexity of time and so forth, with the specified algorithmic complexity, because list packs are ON, so it's linear time. However, when you have a few items, you can abstract away this and you can consider you are still constant time. Okay. So basically each node in the Radics tree, but I should tell you what a Radics tree is. So the Radics tree is a radix with shared prefixed. You have this basically each of the next of the child nodes represent different groups of bytes that describes the key. So basically the Radix tree is not like other trees or log the logarithmic of n data structure, but is an O1 data structure, constant time access. But at each node, then we have a Listpack in the stream with many items of the stream. And because of that, we can do very interesting things. We can specify the number of fields and the fields of the last entry that we saw, of the first entry that we saw in this blob that contains many entries of the stream. This way, when we see other items that are the same, we just set a bit flag to say, look, this data structure, this new entry in the stream that I'm seeing is exactly the same as the previous one from the point of view of the field structure, like here. It's always the same, ppv1, ppv2, so why I should store this again? And in this way I just store the values without the keys of the next items. Of course, at this point, the node, after some entries are added to this node, it becomes too fat and we have to create a new node, but this doesn't matter. I don't know how many we... Okay, stream Listpack max size. It's so big. Okay. This is the pre-allocation. Circumvent allows it. Okay, this is not this. This is not the true limit. The true limit is a different one, and right now I don't know where it is. To be honest, not max bytes. Okay, stream not max bytes. I don't know what is the value of this. But anyway, you get the idea. Basically, at some point, it gets split to another macro node and so forth. But it's not just the reason why we have a so efficient encoding. Also, Listpacks are very smart at compressing data. So basically, we have the tree, which is the Radics Tree. And then we have each node, which is a Listpack. And the Listpack, I will show you this very nice design document that I wrote in 2017 together with Oran Agra and Yuval Inbar, my colleagues at Redis Labs back then. And even now, I still work with Oran. And it is very interesting how this works. For example, this is an evolution of something that we already had, which was called zip lists, but this has a lot of good things, but I want to show just the memory saving tricks. For example, if you have a number and you are appending a number like the one that I am appending here, like this number here, 1842. It's up to 16 bits, so I set this bit here, and the next field will be just a 60-bit signal number. If it's a very small, sorry, this is strings, tiny strings. Okay, this is okay. For example, small numbers are represented like that. Just there is the 0, and then there is the bits of the small number, and we use a single byte for this number. Okay, for example, the string 3 and the string. Technically, Listpacks only handle strings, but if these strings appear to be representable as numbers, we exploit this, because this is extremely common. Because as you can see, actually, from the point of view of the logical data structure, we only have strings. You see, this is a string, but this is a string, but this will be encoded as 0 and all zeros. It's just 1 byte, or will be a 1 byte even in this specific case, but I will need a terminator, so it will be 2 bytes, and instead is a single byte, and so forth. Also, the strings are have many tricks where I can just say this is the length of my string, and the bytes that will follow are just from 1 to 0 to 63, because the empty string is also encodable, and so forth. Another magic of this data structure is that you can traverse it also in reverse, because there are list data structures that we want to traverse from the tail to the head, so it's very versatile, and it's super cool. And because of all these reasons, we have this magic of very little memory usage. If we do some computation here, if we have 49 bytes per entry, and every minute there are 15 seconds, and 1 hour has 3600 60 minutes, and there are 24 hours. In a year, I will use 1, 2, 3, 1, 2, 3. In a year, I will use 100 megabytes, which is extremely acceptable to have so dense time series, and I slowly can delete if I want the old data. There is also the ability of Exad to trim. There is Xtream as well. Which can trim given a threshold, and so forth. There are many things, but still I can run this for years and years. Even in this computer here, this terminal is open on an old MacBook. Usually I sell my old MacBooks, however this was used by other family members for some time, and then I realized it's too old, too old, let's use it as a server. And it has 16 gigabytes of memory, and it's a dual core something, Intel something i7, I believe. So this will be the inverter server, which is better than other. It has a battery. If the power goes down, I can still use it. So basically, there is a lot of advantage. It has plenty of RAM. And this is what runs the Redis server. This is its address, exactly, and it works very well. So if you don't know Redis Streams, I suggest you giving a look. Also, if you have an inverter and want to hack a bit, it oftentimes don't care about the brand that it shows in the label. It's probably some Chinese production, and you will find plenty of documentation, and oftentimes some Python library, which also provides the implementation in order to talk with the inverter if you want to do something like that. Maybe I will release this code, but it's code wrote in order to work fast, not to be particularly useful or configurable. It's very ad hoc, but maybe I will release it. Okay, enough for today. See you next time. Bye.